Hi, welcome at this session about the Delphi Object Pascal Parallel Library. I'm Danny Wind, and in this session I'm going to show you how to use tasks, futures and parallel for loops to create responsive apps. Let's start with tasks. Tasks are like a parallel procedure, a procedure that runs in parallel to the main thread. And tasks are held in a queue, and that queue is managed using a master worker pattern. So there's a master thread actually looking into the queue, and this master thread then allocates threads from the thread pool to actually do the work for your task. And the thread pool has a number of threads that's based on the number of CPUs that's available. So if you got like 4 CPUs available, the thread pool may actually have only 4 threads available. That means that a maximum of 4 tasks will be executed in parallel. Let's look at the tasks using an example. We're going to use a multi-device application, and I'm going to place a button and a label on that. I'm going to use the button to actually start a task, and then I'm going to show the result in the label. Let's increase the sizes a bit so you can actually see what's happening. You actually do that in text settings, because in FireMonkey all controls are styled. Okay, first we need to show you what the effect is when you don't use the-task. So if you're not using the-task, you have to actually wait for some long-running operation to end. So let's assume that we'll initialize label text, and then we'll do some long-running calculation, that takes some time to complete. And that calculation, I'm just going to simulate it using a sleep. After the sleep, I'm going to get a random value, and that random value I'm going to put into the label. Okay, just like that. I'm using toString here. It's a new way to do a int toString. Let's run this and see what the effect is. So if I now press the button, the application is actually unresponsive for a number of seconds, for 3 seconds to be precise. In order to actually show that the application is unresponsive, we can add a scroll bar with an animation. So just add a float animation. You have to actually nest the float animation underneath the scroll bar, and then you can actually set the properties. We're going to use the value from 0 to 100, and let's do a duration of 1 second, enable it and loop it. Oh, and auto reverse, of course. Okay, let's run it again. Then we'll see the scroll bar going from left to right. And as soon as we start clicking the button, it will stop. So the user interface is unresponsive during that time. That's something we don't actually want. So what we're going to do is we're going to embed the long calculation in a t-task. Let's rename the button to button task 1, because we're going to add some other tasks. And let's rename the label to label task 1. Okay, and in the button task I'm going to add a t-task. So let's rename label here and add a t-task. Uses system threading. And system.threading is where you can actually find t-task and the other threading features from the Object Pascal Parallel Library. We're going to embed this part, the sleep and the L value, in a t-task.run. A t-task.run has a number of options, and we're just going to use one with an anonymous procedure. Begin end. An anonymous procedure is a procedure without a name that you can actually add as a parameter to a function call or a procedure call. Okay, any t-task.run, you get a sleep, 3000 L value random, and that's going to run in parallel. That means that the label task1.text won't be executed if you put it behind it, or otherwise, well, It will be executed, but it will have a L value which that has no value. So we need to actually put label task1 text inside the task run procedure, and then put that inside and synchronize, because we need to synchronize it with the main thread, because label task1 actually has a visual appearance. It needs to be synchronized, otherwise the canvas painting will get out of whack. Okay, let's run it. You see it's still responsive, scroll bar still running. That's more like it. Okay. Now we know how a task works. Let's take a look at a future. A future is like a parallel function, and a function is a procedure that has a result. So a future is actually a task with a return result. It does have a weird feature or unexpected feature. That is, if you ask for the return result and the future is not finished yet, it will actually wait in that thread you're using for it to complete. So if you use a future from the main thread and the future hasn't finished yet and you actually ask for the result, the main thread's gonna wait. So you got a wait state. And it's actually a wait state in getValue, as you can see in the code on the right side. Let's look at a simple example of a future. We're going to use another multi-device application, and we're going to add a button again, but this time we're going to add two buttons, and with the first button we're actually going to start a future, and with the second button we're going to request the result. So the first button is the start button, so it's a start future string. Let's copy it, and in the next button we're going to request the value of the future string we just started with the previous button. Okay. In the start, we need to use system threading, of course. Let's add that one. And then we need to use a future. A future is actually a part of a t-task. It's sort of a specialization of t-task. And it returns an iFuture. So we need a placeholder for the iFuture, and the iFuture is what actually holds the result of the future. And iFuture is a generic interface. So just put some brackets here, and I'm going to determine what type we're going to return here. So t-task future, let's return a string directly. And that means that we have to define a function that actually also returns a string, and that's an anonymous function, a function without a name. And in that function we're going to do a sleep again, so some calculation that takes some time. In this case a sleep, and then we're going to add a value, a result value. Let's say hello code rage. Let's add a number as well, because otherwise we won't see the difference between the strings. We click multiple times. Okay. Let's not forget to modify the future string interface. It needs to be of the same type. And we need to move system threading up, I see, because it has some red stripes. Okay, let's move that one up. And it should be there. And the second button, we're going to request a future string. And we're going to request it using the interface that was returned when we started the future string in the button 1. And that says future string value. And that's all there is to it, really. Let's run this code. And when it runs, it's going to start that function, use a sleep, get that result, and then it's going to display it on the button. Okay. And we start it and we request it before it's ready. It's going to be unresponsive for a little while because it takes 3 seconds. So we start it. We can actually move the form until we request it. And if it's not finished yet and we request it, it's gonna pause the form. That's all as expected. So we've got a future string using an anonymous function that returns a value. So future is just a special version of a task with a wait. And knowing that a task can wait means it can also do task chaining. That means that tasks can be chained together. Tasks can actually wait for results from other tasks or futures. And this uses task.wait internally like the future does. And t-task actually has a wait for all, so you can wait for all the tasks that are in an array or wait for any. It means you wait for one or more of the tasks to complete inside an array. This is a type of a fork and join pattern. And we're going to take a look at an example and how to do that. Let's take a look at task chaining using an example. We're going to use the same code we used just now for task with a button and a label. But instead of just one task, I've added 5. And it's doing actually the same thing as the first demo. But run task is now encapsulated in a procedure. And that procedure actually does the task.run with the anonymous procedure and the sleep and the random. So it's the same code, but just encapsulated in a run task procedure. And I'm going to add a tasks array of iTask. And I happen to know there are just 4 of them. And that array is going to be used to communicate with the tasks that may be running. So run task needs a parameter of a task of type iTask, and it's going to be filled with the t-task.run interface. The t-task.run actually returns the interface to iTask. And it needs to be a var, of course, so it's a var iTask. Let's change that here to a var. Okay. And then we need to use a task in each of these using all tasks 0 and all task 1, and so just gonna input the parameter, and the parameter is gonna be an array position. So for each and every task we now have a task interface available. Let's just run this to see how this works. It's not different from the first example of a task. Just we have more buttons. And they're going to run in parallel. What we're going to do now is add a button and do some task chaining. Let's combine task 1 and 2. So let's add a button and a label and combine task 1 and 2 using the interface for task 1 and 2. Let's put this one to a somewhat larger size. Okay. And let's add them up, or just add the texts. That's easier. Task 1 plus 2. And there's a label, and the label is also task 1 plus 2. Task 1 plus 2. Here we go. Now for the code. We need a different array because we just want to make it dependent on task 1 and 2. So task 1 and 2, task 1 to 2. I'm going to pass that array of those 2 tasks to the wait all method of a t-task. Let's initialize the label task1 plus text to an empty string and then start the task. Task 1 to 2 is number 0 is actually the first task and number 1 the second task for all tasks. So now we've got interfaces to the first two running tasks and behind button 1 and button 2. And just start a task run as usual with an anonymous procedure. But inside this anonymous procedure we're going to wait for task 1 to 2. And we're going to wait for all of those 2. It's just 2 of them. So task 1 to 2. You can also add a timeout if you want. We're not going to do it here. And then we're going to set the text to the results of task 1 and 2. And those results are actually inside the labels. Label task 1 and label task 2. Okay. Looks about right, but it's not yet completed because we need to add this one into a synchronize, because it's actually communicating to the FMX framework, to the visual part of the FMX framework. So we need to synchronize it. Otherwise we'll get into canvas problems. Things will be painted properly and things like that. Okay. Well, we're done. Let's run it. Now if I start the task in that one, it's going to wait for the result of task 1 and 2, and then it's going to display 8 plus 0. Okay, let's try it again. Here we go, 0 plus 5. It's actually got no wait state, so it's got no waiting time, that's it. So it's 1 plus 5. I've got a more complete example of task chaining. I won't bother you with all of the code. Okay. And let's get a task 1 plus 2 with a wait for all. The same as we just made. But it also has a let's look at all tasks. All tasks was the array of iTask, and we're going to use that one to actually do multiple tasks chaining with a wait for all tasks. And that task wait for all tasks, we're going to use that in the sum. So we're going to display the sum of all results. Let's run them all. You can actually see the scroll bar running, so it's all in parallel. And the sum's 27. Let's recalculate. So I can actually calculate it myself. Yeah, that's correct. It's 24. And that's 9, 17. And that's going to be 28. Okay, if you actually start them at random, you'll have multiple tasks running, but I'm actually overwriting the iTask, so you'll get some weird results. You shouldn't do that in this way, but it's a nice example of task chaining. And that's about it. So you need to use ttask.run as usual, create a procedure, use wait for all, and use the tasks array to actually communicate the tasks. Next we're going to look at a parallel for. Now parallel for actually splits a for loop into pieces that run in parallel, and behind the screens it uses tasks actually to execute those pieces. And the pieces are actually used, the pieces are called strides, and we will see how strides work in a nice demo with painting rectangles. If you use a parallel for the first time, the parallel for actually waits for completion. So if you use a parallel for simply in a main thread, the main thread will hold until the parallel for is completed. So if you've got a parallel for with 1,000 items, it's going to wait a while. And you could use a task to embed it in a t-task if you don't want it to wait in the main thread. Let's first make a simple example with a for loop, and based on a blank application. I'm just going to use a simple parallel for loop with a memo. I started, of course, with a button. Trusted all button, not a memo. We need a memo. Okay, and that for loop is going to display the number 0 through 9 in the memo, but because it's going to be a parallel loop, the result is maybe unexpected. So it's a parallel for, and we're going to start it with this button. Okay. The parallel for requires system.threading again. So let's add that one to the users clause. Here we go. And then the parallel for. Let's first clear the memo. And then we're going to add tParallel.for. And this isn't very helpful because you get a lot of examples of for loops you can actually add. And it's going to hide my code. And it's also going to add an ampersand. Before the for, you don't actually need that one. You can actually remove it. Okay, we got a parallel for from 0 to 9. And it actually executes a procedure, an anonymous procedure, with a parameter index. And that index is going to have the values 0 through 9. And the anonymous procedure is going to be executed in parallel. That means that if we want to do something in the main thread, we have to synchronize or queue it. So if we want to display something inside the memo, we need to queue it. Instead of using nil, I'm actually going to request the current thread's ID. It's nicer this way, but it's not really necessary. You could have added nil. Memo1.lines add and add some string. We're going to actually add the index to string. So you can see the values 0 through 9. Well, let's run this. Okay, let's start it. And we've got the values 1, 0. Hey, it's out of order. That's actually how it's supposed to be, because the parallel loop actually runs in parallel. And that means you cannot rely on the order of execution anymore, because each item, 0 through 9, is run in parallel. And the index to string is actually the actual index. We've got a nicer example of how this works. It actually demonstrates the stride as well. The normal for loop is just 0 through 99. And that's going to execute in order. And the normal loop, how does that work? It just clears the rectangles. It has a from and to, and an array of rectangles. And the array of rectangles is actually used to paint the rectangles. We use a ttask.run to asynchronously execute the for loop. If we remove the ttask.run, let's get it out of here, then we won't actually see the progress. That's why we're using a ttask.run. Let's edit it here, remove it here, and let's see how that works. Now if we now run this, you won't actually see anything, because it's just running the for loop, and after it's finished, it's going to display the entire result in one stroke. So that's why the ttask.run is there. You want to see the progress. Okay. Let's undo all that I did. And let's run it again. Now we're going to add, and now we're going to run the parallel for loop with a stride of 10. You can actually see multiple colors. Each color is its own thread. And because you can see colors repeated, you can actually infer that tasks are being run on the same thread, on the blue thread or the green thread or the purple thread, and they're run out of order. So I've got a stride of 2. You can actually see the higher items being executed first. And a stride is, what a stride means is that it's run in batches of 2, in pieces of 2. But it doesn't mean it's run on 2 threads. So if you get a stride of 10, you can actually see 10 items run consecutively. And if you undo synchronize, the painting is going to go, because it's no longer synchronized with canvas. So we need to synchronize. Okay, let's take a look at the code. For the parallel 4, it's quite the same as the other one, clear rectangles from to, and with the addition of a stride. And now we do a tParallel.for with a stride, and then a from and to inclusive, and an iterator event, which is just a procedure. And this paint rectangle procedure, it looks if it needs. It looks at the checkbox to see if it needs to use synchronize, if you wanted to use synchronize, because you actually need to use synchronize. And it uses the current thread ID to calculate a color. So each thread has its own color. Let's make a stride of 20. So we got 20 numbers in one task, and those tasks run in parallel. And every time it's run, the queue is actually the threads are actually recreated, so they get different colors, different thread IDs. That's it. How do you use these techniques to create responsive apps? And what is a responsive app? Well, I'm not talking about responsive design here. Responsive design means that the user interface actually gets resized depending on form factor or device size. I'm talking about a responsive application that never blocks, that never waits. So you've got no user waiting for some action to complete. The user can actually just click on buttons, do things he want to do, and you get immediate feedback. It's responsive, it gives you a great user experience, and the user actually has a perceived speed because of that, because you can actually just click everywhere and do things. And the perceived speed doesn't actually need to be actual speed, because things can still take some time. It just doesn't block the user interface. So you need to get your data and run your operations in parallel. I've got two examples. The one is the threaded REST. In the threaded REST demo, we're going to use REST request, which is slow, more or less slow. And it's going to do a REST request to Discogs database, and it actually has a number for every artist. And I've abused tag to add that number. And then I'm going to execute the REST call. And the REST call is going to use threading or not. And the not threading uses the REST request from the user interface. Does a normal execute. So I use the REST client. It uses API.discogs. REST request actually request artists based on ID. And the REST response will get the text result from the REST request. Let's run it. So I'm going to request Katy Perry, John Legend, Coldplay, Rihanna, Wende and Fink. Actually, it doesn't take all that much time, but it does block the user interface. As you can see, the progress bar actually stops if I click a button. And if I use threading, it just continues on. I can actually just click buttons everywhere. It will just work. So if you use threading, the user interface stays responsive. And it's not that complicated to actually use threading here. We use the task.run, and we place the do REST call inside a procedure. We actually need to create a local client request and response, because we're gonna execute multiple threads at the same time. And then we get a feedback from the REST response as a result. And that result needs to be communicated to the memo using the same synchronization, because the memo needs to be painted. Okay, let's run it again. I can actually move it here, and if it's threaded, I can just click buttons and move the form. And you cannot really move the form. Well, it's too fast. This Cox is quite fast today, so it only takes 500 milliseconds to get the artist. That's faster than usual. But you can actually use this demo at home. So the source code's in the zip file. Let's take a look at the other demo, the threaded database. In this threaded database, what I have is a list of books, and if you select the book, it's going to request the content of the book. So if I click it here, it's going to get the content, and that's going to take a while. And there it is. And as soon as the content is available, it's going to place an accessory object. That's the eye on the right side. But during requesting, during the content request, it's unresponsive, and I don't like that. So let's make it responsive. Let's look at the code. Request to display content based on a marker, and the marker is actually an accessory type. So if it's more, that means it's not yet there. Mark as it's on its way, so set the check mark and request content. And request content actually gets the content in line with the main thread at this moment. But it does use a data module thread, so I'm cheating a little here because data module thread is something I made beforehand. It's not threaded at this point. It's not threaded. I need to store the content in a cache. I'm using a client dataset cache, and then I'm going to mark it if it's finished, and then update the accessory item. And the detail is actually an eye. The eye you just saw in the user interface. Just to show the data module thread's not threaded yet, it's just a query. But it does actually use the local connection in data module thread, and we actually create a new instance for each thread or each task that we're going to run. So we're going to embed this stuff in a t-task. Let's run it again to see how slow it is. Yeah, it's quite slow. And there's the eye. So eye is the accessory item detail. And after you click it, you can actually request the content. Okay. Let's make this app responsive. This needs to be outside the t-task, and this stuff needs to be inside the t-task. So I'm going to add a t-task that run with a procedure, and I begin, and I'm going to embed the all loading and updating user interface inside the t-task. Okay. Now we need to split loading the content as well and the user interface. And we're using system.threading, of course. Otherwise it's not going to work. Okay. We need to split loading the content and user interface updates. I'm going to add these as local variables because I don't want them outside the thread. I don't want them available outside the thread. It's not necessary, but it's nicer this way. Okay, the first part is just requesting data, so you can actually run that in a t-task. So the data module threads and requesting the content. Because we create a new data module thread, we actually create a new FireDeck connection for each task. And that's just what we want. But this part is using the main thread data, the data module main and the memo detail. This we use in the main thread. So we need to synchronize it with the main thread. And the last part is actually not the part that takes a lot of time. Just takes a couple of milliseconds to add stuff in the cache and then show it in the user interface. Requesting the content, that's what takes the time. Okay, let's run it. And now we can just click on something, get a check mark because it's loading in the background, and there it is. So the content is now available. But now I can just use the user interface at any point I like. Just add multiple books, switch between content and book. User interface is always responsive, and in the background it's actually requesting my content. That's more like it. No more waits. And because it's using content, because it's requesting content in parallel, it's actually faster as well. Okay, let's take a look at the how this works. T-task run, thread synchronize as usual. I'm going to add open another version. Okay, no, let's not save that. The other version actually allows you to cancel requests. So next to the more type, that's sort of a starting point. If there's a check mark here, I want to be able to cancel pending requests if possible. And that cancel request content actually uses a task array. The same task array we made earlier, which is just an array of iTask. And that array is filled with tasks. As soon as you request content, a task is created and placed in the task array based on identifier. So if there's a task for that identifier, and if the status is waiting to run is the status. That means that the task has not been allocated to a thread yet. And then we can cancel it. Okay, let's try that. You have to be fast because it's actually running in parallel. And yep, I just cancel. Oh, I can only cancel 2. The other ones are available already. Yep. Okay. How to cook an egg. It's all fake data, of course. It's just a demo. And the demo is of course available in the zip file. Okay, that's it for now. Let's do a Q&A. Are there any questions? And if there are, you can just use the panel in your webinar on the right side. You can ask us questions. The video presentation will be made available by Embarcadero after Code Rage 9 is completed. But the materials for this session will be made available directly. You can use this link on this page. I think David will just leave it here for now. So you can actually just copy it. Well, copy it. You have to write it, probably. Okay, thank you, and on to the Q&A.
Well, thank you, Danny, for that great session on the new parallel programming library in XE7.
Yeah, thanks. It's been great to do these kind of sessions.
Yeah, it was good to see all those great demos and examples and stuff that you provided there. There have been a lot of questions about that coming up to this.
Oh, thank you.
Is there anything you want to add to your session, or now that you've seen it, you want to maybe comment on?
Yeah, I sort of used Synchronize heavily in my demos, and although they work correctly, some of them would have benefited from the use of queue, because queue doesn't actually wait for the main thread to process the synchronize. And that sort of prevents deadlock situations if you use a wait for all from the main thread. So queue is a better option in some of the demos I made.
Okay, yeah, that's one of the things that's tricky with demos sometimes is coming up with something that's simple enough to show code demo without making it, and still making it the best way to do it. So, but that's good to know. All right, so I'll go through some of these questions here, and You already answered some of them in text, but we'll go ahead and go through them again. You can elaborate on it.
Okay, thank you.
In the old tthread class, you have the execute method that would control the work. Would the procedure that is declared here be the same? And if the execute controls, or if execute controls lots of the other processes, for example, by using semaphore, could control flow of other procedures and threads do other things?
No, it's sort of similar. Ttask.run, you can compare it to the thread execute, but ttask.run is just more than execute because it's also using a thread pool to do the actual execution, and you get a better CPU load balancing because of that. On the other hand, the mechanisms you use in execute, you can also use them in ttask.run, so you can still use semaphores, critical sections, and you can actually do a wait for all, and then use a fork and join like pattern that I used in one of the demos. So they're similar. Yeah, they're mostly similar.
Yeah, I think that's one of the I guess maybe the important differentiations between tthread and ttask is tthread was actually a thread, whereas ttask is something that's going to be processed by a thread pool. So we're dealing with the units of work instead of the actual threads itself.
Yeah, we are. And that actually makes it easier to write multi-threaded code because you don't have to worry about starting too many threads at once or things like that. The thread pool will even that out for you.
So the number of tasks doesn't, you don't have to worry about how many threads you have or how many CPUs you have before you start creating tasks. Is that correct?
Yeah, that's correct. You don't actually need to request or take anything like that into account. It's just going to be scheduled and it's going to look at the CPU load that's originating from the tasks that are already running and just balance it out.
So there's a question here that says, is there a way to know how many CPUs are available and can we specify how many to use in the thread pool so that we can ensure that there's CPUs left over for other processing on the system?
Yeah, you can actually use a custom defined thread pool. So you just create one your own and then use that thread pool for your task. So you can actually say that this task needs to use that thread pool. And that custom thread pool, you can customize it using some of the settings inside the thread pool. And you can also request the CPU count using thread.get CPU count, or is it processor count? Get CPU count is system level, I think. It's tthread.processor count.
Processor count.
The processor count, yeah.
And does that report physical CPU, physical cores, or does it report 2 for hyper-threaded, or how does that work? Do you know?
I believe it actually reports the logical CPUs. But
logical CPUs.
To be honest, I'd have to check.
Okay.
Because I don't actually need to use that because the thread pool actually is self-optimizing. So
it's one of those things that you probably don't need to go down that path unless you really know you need to go down that path, is what you're saying, because it does optimize. Okay.
Yeah, it's the thread pool is sort of self-optimizing. You can tweak some settings, but it's easy to just tweak the settings like I want maximum 50% CPU, then actually counting the CPUs yourself and then load balancing it on specific CPUs. That's harder work. That's not really necessary. You can just say, okay, I want to have 50% CPU load.
I remember when multi-threaded or multi-processor systems were first coming out and people were going into Task Manager and setting a CPU affinity, and someone came out and said, okay, most of the time you don't want to do that. Let the processor, let the library, let the OS handle that, and most of the time you do not need to mess with trying to set CPU affinity and such, because you're probably making things worse.
Correct, yeah. And you're also interfering with power saving.
That's true. Yeah. So here's a question. Is the T-task like procedure and T-future like a function?
Yeah, that's good. Yeah, I'd say that.
So T-task is do something, but T-future is do something and then give me the result back.
That's correct. Yeah, T-task is like a parallel procedure. It runs in parallel. It gives you time to do some stuff in parallel as well, whereas T-future is like a function returning a value at some later time. So they're a parallel procedure and a parallel function, really.
I've actually worked with functions in the past where it was very manual with its own threads like that, or not functions, futures. And having this kind of baked into the library is a huge benefit. Futures are one of those things that you may not have run across times when you need them, but when you do need them, they're such a huge saver to have.
Yeah, it actually makes it very easy to do a sort of fork join kind of thing.
Oh, yeah.
Where the next future is waiting for the previous future to complete or some other futures to complete. You can just make mathematical equations with them.
Yeah.
If you want to.
Sure.
Which makes it very easy to read, by the way.
Yeah, that's a huge thing about having the library like this. Is it makes it easier to read and maintain your code, which is important. So, someone says, do you have any guidance for debugging for someone who's new to multi-threading?
The Delphi IDE actually has thread debugging, and that allows you to debug tasks like you would T-threads. That's one aspect. The other one is just avoiding bugs, which is easier said than done.
That's a good advice. From now on, I'll just write bug-free code. Thank you.
Yeah, that's a good one, right? No, it's actually a true advice. If you make your threads free of serializing dependencies, that means that data is not shared among main thread and your task or between tasks. It's a lot easier to write multi-threaded code that way. It will cost you more memory, but memory is cheap.
So you're saying instead of trying to pass data back and forth, maybe do it through a future where it returns the data when it's done type situation? Or what would be the best way to do that to avoid passing data back and forth?
Actually, I had an application that benefited hugely from just duplicating data. So we had a large data set, largest data set about 60 megabytes, and just duplicating that one 8-fold and letting 8 threads run in parallel without any dependencies between them created a simple to read code while getting maximum performance. And the other solution would have been using semaphores or critical sections to actually share the 60 megabytes of data between threads. And that's a lot slower and a lot harder to maintain.
Okay, that makes sense. It's one of those things that sometimes we try and optimize things before we need to, and we just make things more difficult.
Yeah. You're thinking about, I have to protect this piece of data, and well, you can probably just duplicate it.
Don't worry about memory unless it's an issue.
Unless it's an issue, yeah. If you want to duplicate like a terabyte of data, that's not going to work.
What about exception handling inside the tasks? Are there any special care needed there?
There's a special mechanism inside tasks that actually bundles exceptions that occur during the runtime of a task. And that bundle will come out as one exception with sub-exceptions and bundled exceptions inside it at the end of the task. So you can do the exception handling outside of the task in the main thread, or you can just do exception handling inside the thread. That's possible as well.
So you could do like some temple try except for specific exception cases in the thread, but then otherwise just take care of the big bundle when the thread's done?
Yeah, that's correct.
Is there any support in the new parallel library for fibers, for example, lightweight cooperative threads?
That's a good question. T-Task is actually using T-Thread internally, and T-Thread doesn't use fibers. And there's no fiber support currently. I don't think there will be any fiber support because it's also operating system dependent. If you want to actually use fibers on Windows, you could do that, but it's not in T-Task. There's no support for it yet.
So fibers are a Windows-specific feature then, so that would only work on Windows?
More or less, yeah. There's a Mac version of fibers. I'm not aware of any iOS or Android-specific fiber support. So it would probably hinder multi-platform development. Okay. So T-threads are a better option.
Currently using DevExpress's grids with lots of data. Can I use this threading/parallelism to load data in the background for the grid so it can speed things up? It's currently quite slow, and the interface is not responding while the grid loads the data.
That's a yes and a no. You can actually load the data in the background into a in-memory dataset, but the actually loading into the grid, you'd have to do that in the main thread because the DevExpress grid itself, it's not fully thread safe. It's VCL based, so it's not fully thread safe. The DB grid actually the Quantum grid actually has some synchronization procedures. So you can do some stuff in the background, but generally it's not thread safe.
Okay. Could you use this with blocking Indy sockets in order to keep it from blocking?
Yes, definitely. One of the demos I made, the REST demo, actually uses Indy internally to do the REST calls. So I'm actually requesting REST information using Indy sockets in a T-task. So yeah, definitely.
Great. How to refresh data from a DB-loaded parallel? Okay, if you load the database in parallel, how do you refresh the data and not have to get the entire data set again?
I'd use a client dataset or FD table and then merge the two. So you've got like an in-memory dataset for your display. It has a partial data, and then you request the other part in another in-memory dataset, and that just merge the two in the user interface dataset.
Okay.
So it's just using in-memory datasets, really.
That's a great idea. It says, just started an application, thought about using threads, but registering data in some tables are dependent of completion of registering data in other tables. Seems that this could be a function of using wait for certain threads to signal different steps to other threads, like populating different objects that must wait for initiation until other are already present in the database. Does that sound like a good way to do this?
To me, it does. You can actually use wait to let tasks wait for each other. You could also use futures, and just use futures to sort of string them together for the results. But yeah, it will definitely work. You can also use the semaphore's critical section method that you used to in T-thread, but it's a lot easier to write code with wait and wait for all. It's easier to write and maintain code that way, so I'd use just wait.
What sort of memory management dependencies do you need to be aware of in a multi-thread application, and how do you deal with those?
There are some contingency issues in FastMM. I'm not sure if you mean that. It automatically set is multi-thread, but even then there are some, if you do a heavy memory allocation in FastMM from multiple threads, it's gonna get ugly. And when using the other memory models for Android and iOS, you're actually using Arc, and underwater that's just gonna do a malloc. So they'll just work because it's thread safe. So I'm not sure if you mean that, or if you mean serializing dependencies, that is sharing data among threads. You could also mean that, because in that case you have to avoid serializing dependencies, so you don't have data shared among threads, and that means you don't actually have to use semaphores or critical sections or waits or things like that. You can just have the threads running freely with maximum performance.
Okay.
Either one of those, I think.
So when it comes to using Synchronize, do you have any tips about how to use it to avoid deadlocks?
I used to Synchronize in my demos as the last call in a T-thread or a T-task.run. If I had used a wait for all in the main thread, I would have hung my applications, my demos. So, but fortunately I used the T-task.wait inside T-task, so that's not an issue there. Because Synchronize actually wants the main thread to handle whatever you synchronize before it will continue. So it's sort of, the T-task is actually waiting for the main thread to complete the synchronize before it will continue. And if you don't wait for that T-task, it's going to wait indefinitely. In that case, it's better to use queue, because queue will sort of put it in a queue like the thread queue, and then continue the T-task and complete it. And that will avoid deadlocks.
Okay, so if you're better off using a queue and then Synchronize to avoid deadlocks. That's probably good advice.
Yeah, that's probably good advice.
In
most situations, queue is better.
Yeah, start with the queue, and if that doesn't work, then that's when you can start getting down the Synchronize path.
Yeah, if you know what you're doing.
Yeah, if you know what you're doing. And the reality is most of us don't usually know what we're doing all the time.
No, queue is probably safer.
Queue is safer, okay.
In my code as well.
Okay, I think that's it for the questions, unless there's anything else you want to add to your great session.
Well, nothing to add to the session. You can actually download the source code and the link provided in the presentation. It's available on a website link. Other than that, thanks for listening to the session. It's been great fun.
Great. Thank you so much, Danny, for putting this together.
Thank you.